Okay, we're going to continue on with our exploration of finding volumes using integrals. Okay, this is really the bundt cake problem. I'm sorry that I called it the other problem the bundt cake problem. But here's the idea. We've got this region, and it's the region that's stuck below this parabola, the 3x minus x squared parabola, and the x-axis. And we're going to revolve it around an axis, and the axis is going to be the line x equals -1. So I want you to imagine taking this little piece, and it's hinged at that axis line, and when I rotate it around, it would create another hump right there, and here's our bundt cake. What is the volume of deliciousness embedded in this bundt cake? Can you see the bundt cake from my drawing?
I think you should bring one in just for like a good.
Well, I mean, the book has got a perhaps better drawing of the bundt cake.
It also looks
Does that look a little bit more clear with the shading?
Jello.
Yeah, it could be like a Jello mold. Okay, so how do we calculate the volume of this? Well, our plan of attack is similar to what we did before. We're going to try to create an expression of area for some particular value, arbitrary value of integration. Now, I want you to see that the cross section of this bundt cake again is going to be a circle with a hole in the middle, what we typically would call a washer. And that this washer has area. The area of the washer is a big circle, which I may write down as pi big R squared, minus the little circle that we're going to subtract out of the middle, which we may put down as pi minus pi little r squared. That's going to be the area that we're going to use for this volume problem. The volume is going to be the integral of this area times a little bit of thickness. Now I'm going to hold my fingers like this, because the thickness of that washer is in that direction. Let's pretend it's thicker. If I'm going to grab it, I would grab it like that and hold it like that, like it was a frisbee. I'm doing a lot of this because the orientation of my fingers makes a difference. How would I measure the difference or the distance between my fingers? Would I measure it as a distance in the x direction or a distance in the y direction? And that's important because that means that this differential is dy, because that differential represents that thickness of that washer. That also means that my area has to be written as a function of y. For some given y, what is the cross-sectional area? For some given y, what is the cross-sectional area of that bundt cake? Well, let's see if we can attack it piece by piece. Let's see if we can say for some given y, what's the value of big R? This is awkward, isn't it? For some given y, do we have an easy way of finding the value from here to here? The answer is not easily. And why do I show you something that's not easy? Because there's probably an easier, different method to do this problem. Okay. Can I go back to the previous problem for just a second? When we did this problem, this was the problem that we had called the bundt cake problem. Right? I want to go about why this problem was relatively easier to do. Is that right? This is cosine x. This is y is equal to sine x, right? And what we're revolving this around? Around the x-axis. Correct? Volume was pi, and in this case, big R squared was the distance from here to there, which was cosine squared, and then we subtracted out the pi little r squared, and the little r squared was sine x squared, and the thickness of this washer, if I grab it like this, dx. And what range of values does x take on? Well, the smallest value of x for this is 0. And where was the intersection of those two curves? Pi over 4. Okay, so that problem lent itself to being able to write this pi big R squared minus pi little r squared because the two edges of the surface were two different curves. But we have a total fail on that with this problem because the two edges of that washer are both on the same curve. So here's what we do. We start over with a different plan of attack. Now, are you familiar with Russian dolls?
Yes.
Yeah.
What are Russian dolls?
There's little tiny ones.
Well, you start with a really big one,
Yeah.
and you take the head off the, and what's inside?
Another one.
Another one, and you take it out, and you take the head off the next one, and what's inside? Okay, and you can do that again and again and again, all right? But the big idea is that they fit inside of each other. I want you to imagine, here we go, that I have a cylinder. Do you see that cylinder?
I see that you drew one, but I don't understand why.
So, just bear with me for a second. There's one cylinder. Can you imagine me drawing another cylinder that's just on the outside of that cylinder? Let me do it in blue. This one's a bigger cylinder. The red cylinder sits inside the blue cylinder.
And this is around.
This is, okay, let's say, taking, for example, the red cylinder. The red cylinder, the base of the cylinder is at the same base as the bundt cake. For that particular radius of cylinder, the top of the cylinder is right at the top of that bundt cake on that area. The blue cylinder has, again, the same base as the base of the bundt cake, and its sides go up to meet the very top of the bundt cake as well. Of course, the bundt cake's a little taller there. Might I draw a third cylinder? Might I? This cylinder goes all the way out to here. red, the blue cylinders sit inside of it. Where's the base of that black cylinder? It's the same base as the bundt cake. Where's the top of the rim of that black cylinder? At the very top of the bundt cake as well. Each one of these cylinders, its top is at the bundt cake's top as well. Are they all the same height? No, because the bundt cake is changing in height. I'm getting confused.
Yeah, I think I'm confused about the structure of a bundt cake.
The top of the bundt cake where they have it.
So it's got like the round edges. So like the top of the cake.
Sage? Oh my god.
Is
The
this
top of the bundt cake, like near the y-axis, is there on the bundt cake?
Look here, I thought I had played
Cake on straight, cake on out.
We can, yeah.
I'll bring it back.
Okay, let's try it again from a physical standpoint. I'm carrying the bundt cake, right? Everyone see the bundt cake I'm carrying? What if I did something? I turned the bundt cake is actually glued to the platter. What if I turned it this way and you're looking at it on edge?
Okay.
What would it look like to you?
Like there wasn't a hole almost.
It'd be the outer edge of the bundt cake, like that. There'd be the inner edge of the bundt cake.
Are we looking at it from the top right now?
You're looking at it from the top. All right? Everyone okay that I flipped the bundt cake over?
Got it.
You're all, that's okay. But it's glued to the platter.
Is it edible glue?
Matthias, don't tell me you were the kind of kid that ate paste and
I was not.
good.
I just don't want to ruin the bundt cake.
No, neither would I. Neither would I. All right. Okay, I'm going to draw a cylinder. Now this cylinder is like a paper, it's like a paper, the empty part of the paper towel roll. It's hollow inside. Okay. All right. And if I looked at it from the top, it just looks like a line. Okay. Although not that thick. But I could lift it up and then hold it like this, and you'd see something. This looks like a cylinder, right? Turn it on its edge. There it is. Take it and I put it right there, and it's made so that it's the height of the cylinder is exactly the height of the bundt cake. It goes and all along that edge. All right. Now, why would I be playing around with cylinders? Because cylinders can be made to have just a little bit of volume. Remember, the theme here is that I'm going to write an expression of a little bit of volume, and then I'm going to add up a whole bunch of volumes. Okay, I'm going to make that cylinder. That's what I'm going to do.
So it's that on top of the bundt cake, right?
What?
Even around as you put it on the cake. It's not on top of the bundt cake, right?
It's
It's touching the top.
That's right, it's not cake.
Like where, if cake still existed, like that would it be there?
if I showed you the bundt cake, you would just see this tiny ring of blue right with cake even on either side of it. If that cylinder was in there. At the top, yeah.
I don't understand.
Who wants to make a bundt cake?
Oh my god, I want a bundt cake so bad right now.
Oh, it's like cake.
Just say it. Because the cylinder is even at the top of the cake. I'm so hungry. Right.
It's not at the very top. It's just on the top surface.
Okay. Can I present half of a cylinder?
Yeah.
That cylinder is like coming out of
it the wrong way.
right?
Right.
It just means
The other half of the cylinder
Its height is the
is behind the board. Everyone see the half a cylinder that's coming out?
Yeah.
And the bump cake would be,
You just got. Oh no, restore.
okay, so the bump cake's coming out of the board, right? And this cylinder is embedded in the bump cake and it comes out of the board too. Bunt.
You go to Random Stores and order buttermilk pancakes, they're like butt cakes.
That's actually, my phone has voice dialing, and my neighbor, whose name is Robert Busick, if I say, call Robert Busick home, it says multiple names. Do you mean Robert Buttsack?
Do you have someone named Robert?
No, but that's a phonetic interpretation of his name. Getting back to, okay,
Would it kind of be like taking the cylinder and almost like shoving it all to the space at the bottom?
Yes.
As far as it'll go up until it gets too wide for the cylinder?
that's a very, or like I was chopping down into it, like an apple core. Okay. What I need is a 3D so invent that. All right. So let's talk about the cylinder that's embedded in the cake for a second. Okay? You know what? The cylinder can be thought of as an area. I take the cylinder and I unwrap it. The cylinder looks like an area. If this cylinder has a little bit of thickness, it is an area times a thickness. Area, thickness multiplied together give you a little bit of volume. So let's talk about the area that comes from unwrapping this cylinder. Okay, if this cylinder has a radius, what's the width of that rectangle? If we go from here to there and we get a radius, when I unwrap that rectangle, that radius becomes 2 pi r. This radius forms that circumference, and that circumference is the width of that rectangle. Right? Secondly, this rectangle, which comes from unwrapping that cylinder again, has a height. What height does it have? Its height is actually the distance from the x-axis to the curve. And that is 3x, in this case, 3x minus x squared. The height of the cylinder is the same as the height of the rectangle, and in which case, in that height is the distance from the x-axis to the curve. So, what is our area as a function of x? Well, this part of the rectangle is 2 pi, and for a given value x, what's this distance? Well, I'm x distance from the x-axis, and then I'm an additional 1 from the middle of the rotation. My r distance is x plus 1. The distance of the center of rotation from which the radius is measured to an arbitrary value x, which is in the middle of that one side of the cake. So there's that dimension. That's our width. Okay, our height is my area, and now let's go to the volume stage. The volume is going to be the integral. of all of that mess. And I need a little bit of thickness. How would I grab this cylinder? Like this. So the thickness of this cylinder is a measurement in the x direction. I'm sorry?
3x minus x.
There we go. And now I'm down to one more thing. And that is, what are the limits of integration? What are the values of x that I'm interested in looking at? And a little hint here, we're only interested in the area that we rotated, not the other part that came from doing the rotation. The smallest value of x is 0, and the largest value of x is 3. So sometimes with these volume problems, we don't do cross sections by cutting through and getting washers. Sometimes we do the cross section cuts, but we cut them like an apple core, like a bringing a circular through the middle of it and getting a bunch of inner I'm trying to say how the cylinders fit inside of each other. I'm at a loss for words. Okay, but there we go. There's our integral expression for that particular volume problem. Now, that problem is as soon as we get to this stage, that integral is relatively trivial. I'm not going to spend any more time doing this problem. We got it to the point where we got to an integral, and that integral, if you expand it out, it's just a bunch of polynomials. It's an easy integral. Okay. What I think we need to do at this point is we need more practice. All right? So what I'd like to do is I'd like to try to attack some of the even problems in your book, the ones that I wouldn't be assigning, and I want to look at them. I want to then explore how do we write these area equations that allow us to write the volume integrals. All right? Let's see what I have next here. Yeah. That was another way of attacking these problems, but this problem didn't lend itself to that attack. All right, let's go and do another problem. Let's see which way it lends itself to the attack. All right. Okay, a region is bounded by y equals the square root of x. What does that look like? Okay, I'll do it just like Chris said, complete with the sound effect. The line x equals 4. No, that's vroom. Okay? And the x-axis. So here is the region that we're going to revolve. And we're going to revolve it around the x-axis. What will this solid look like? Like that? Like a bowl? Except on its side? A jujube? Or dot? It's a gumdrop. Last period we talked about raisinets. Now we're going to talk about jujubes. Right? Okay. How would you like to do this problem? We're going to do this problem twice. We'll do it once using circular cross sections, and then the other one we'll use the cylindrical method. All right? Okay, we'll do it. Step 1, we're going to do it using cross sections. If I had cross sections, each cross section looks like a what? A circle. Right? The area of that circle. You know what? I think I'd like to do this. Before we go to the area of the circle, if we grabbed onto that circle, what's the orientation of the thickness of that circle? It's a dx orientation. That means I want the area for some arbitrary x of that circle. See, it's circle, so it's pi r squared. So it's pi something squared. What's the radius of that circle? From here to there. This point right here is x comma square root of x. So this distance is square root of x. So this is square root of x squared. Pi r squared, and r is square root of x. That looks like pi times x. That means our integral is going to be pi times x, and now what we need is our limits of integration. What? 0 to 4. The smallest x value for this region was 0, the highest was 4. I think I can do that integral. At least I hope so. Let's try it. Pi times 1/2 x squared, evaluated from 0 to 4. Check my work, please. Is equal to pi over 2 times 4 squared minus 0 squared. Check my work, please. 8 pi. Check mark. Great. So far, so good. That way it feels a lot more comfortable to you, doesn't it? All right. I'm going to do the same problem again, but I'm going to do it cylindrical. Just so that you can see it getting done on a solid that you feel comfortable with. Here we go. Erase. All right. So here is my region. When I revolve it, I get another region that looks just like it. And here is a cylinder inside that region. This circle is actually on the base of the solid. This circle is riding along the top of the bottom of the bowl if you had lifted it up. All right? This cylinder has a thickness that I would grab this way, a dy thickness. This cylinder, if I unwrapped it, would have a rectangular area which is as long as its circumference. And that circumference is 2 pi, and the distance from the center of rotation up to the edge of the cylinder is exactly y. And I want to write everything in y. So this is 2 pi y, and that's again the unwrapping of the cylinder and its width. The height of that cylinder is from here to there. From here to there. And I want the stuff further to the right to be listed first. 4, minus here. I need to know what coordinate this has. This point right there. I know it has the point x comma square root of x. But that's not helpful. I need to write something in terms of y. Can I call it y squared y? Is that the relationship between its y coordinate and x coordinate? This point right here has an x coordinate of y squared. This has an x. This one over here has an x coordinate of 4. That distance is y, or 4 minus y squared. And now we're to the point where we say, what are the limits of integration? What's the smallest value of y for the region before I started rotating it? 0. What's the largest value of y for this region? This point right here on the corner is the point 4 comma 2, I think, right? Yeah. So from 0 to 2. Now if I've done everything properly, we should get the exact same volume that we got the first time. You don't trust me, so let's go on to the next problem, right? No, I can solve this. All right, there we go. Ready? I'm going to pull the 2 pi out. Integral. I'm going to distribute this y through these terms. And I get 4y minus y cubed dy. And this is going from 0 to 2. Check my algebra, please. All right? Continuing on. 2 pi, the antiderivative of 4. Well, okay. The antiderivative of 4y, 2y squared. The antiderivative of negative y cubed is negative 1/4 y to the 4th. Evaluated from 0 to 2. This is equal to 2 pi times 2 times 2 squared minus 2 to the 4th divided by 2. So there's all of that stuff evaluated at the high end, minus 2 times 0 squared minus 1/4 times 0 to the 4th. Second set of parentheses. And I think we all recognize that this is just a big whopping 0. That gives us 2 pi times 8 minus. Oh, that should be a 4 there. Sorry. That's good. All right. 2 to the 4th is 16. Divided by 4 is 4. 2 pi times 4 is 8 pi. All right, we got the same answer twice. This particular, again, solid region could be done either direction. Some of them, like the bunk cake problem, do not lend themselves to washers. So we end up having to do the cylindrical shells. Yes?
The cylinder always gonna, or like, that way it's always gonna be like, using Y,
That's a really good question. And the answer is no. The answer is, I want you to get into the practice of saying, how do I grip that cylinder so that the way the cylinder gets gripped tells you whether you have a dy or a dx problem. Actually, in the bunk cape problem, the cylinder was a dx. Okay. You see the cylinder coming out of the board? Okay. When I put my hand to grab it, and I put my thumb on the inside of the cylinder and my fingers on the outside of the cylinder, I'm grabbing, and the stuff in between it is the thickness of that cylinder. Okay? And when I grab it that way, the distance between my fingers is in the y direction. In the previous problem, when I grabbed the cylinder, I grab it this way. Now the distance between my fingers is in the x direction, and that's why that cylinder problem was an x problem. All right? All right. I think here's another problem, and this one specifically wants us to try to do it using cylindrical shells. They call them shells because they're hollow and they fit inside each other. Should we try it? What's the worst that could happen? Maddie's watch could go.
Change my watch because the ACT, you know, I have a watch that beeps.
Okay. Well, that's probably a good idea.
Yeah.
I once was a proctor of a room that had someone's cell phone had an alarm on it, and it went off like with 2 minutes left in the math section, and it voided her score, and it almost voided the whole room, and it was really just.
Yeah. I'm happy I remembered.
That happened to me last time. Like the cell phone went off 2 minutes before like the whole test finished.
Uh-huh.
I was so mad.
Yeah, they have a form you have to fill out called a testing abnormality or something. It was bad. Let's go back to this problem. So we start this problem by drawing pictures. How about the picture of this parabola? Yeah. Yeah. Well, I'm going to put some axes on here first. Do we know what these points are? -2 over here. +2 over there. Okay. Now Edmund did this. Something like this. This point right here. Now, 2 would be right here. Well, let's see if we can find out. We've got y is equal to 4 minus x squared. We've got y is equal to x. That means every place I see a y, I can replace it with an x. I get x is equal to 4 minus x squared. Or x squared plus x minus 4 equals 0. What do you mean, Jordan? You can't factor that. Oh, there's no solution then.
Well,
There's no rational solution then. If you want to solve that, what are you going to have to do? You have to. You could throw it in your calculator and find the intersection, or you could use a quadratic. Well, which way do you want to do it? Which way do you want to do it? Either side? Either way? I'll tell you what. You figure out what it is, and I'm going to go to the next step, which is I'm going to revolve it around. Right. Those two curves, x equals 0. Where's x equals 0? Oh, it's the y-axis.
Some doesn't seem right because if that's at 2 where you drew it, if x is 2, then wouldn't y be 0?
Well, here's what's going on. It's like we've got this, x equals 0, this line, and that curve. This is the part that we're revolving around the axis. Right?
So the slope colors.
So that when we revolve it, there's the reflected image, and indeed we get something, if I make it really big, we get something that's snow cone shaped. And so everyone okay with that? Solid. It's like a cone on the bottom and a sphere-like. It's not exactly because it's made out of a paraboloid, but it kind of to the untrained eye it would look sphere-like.
Wait, so
Like
you,
an egg.
More like an egg, yes, more like an egg.
so you had it kind of, so it's rotated about the y-axis.
It's rotated around, yes. The y-axis is going right into the middle of this.
Right, so what about the, I'm trying to picture this, we have the line and then we have the parabola, so how do we know where to rotate?
It told you what it was.
Yeah, but where did you get that line from then?
Well, because it says it's rotating, is revolved about the y-axis. So here's the y-axis there, and when I revolve it around the y-axis, I get this other image on the other side, and I get, I get those.
You don't get that kind of triangular shape too?
No, I made it longer so it looks more like a snow cone. But this line right here is that line right there.
Well, why does it cut off at 0? Oh, okay.
Because this is the boundary. Yeah. All right. So, can I draw a bunch of cylinders in this? Well, here's a cylinder. It starts here. It reaches out to the top of that icy and flavor-filled goodness.
Why did you choose to start it there? Does it matter?
Because, actually, you know what? That's really poorly drawn. Hold on. It's not that I started it here. It should have ended right onto the top of the snow cone. So this cylinder, the bottom of the cylinder is riding along the paper cup of the snow cone. The top of the cylinder is riding along the icy goodness on the top. By the way, that flavor they put on it never lasts long enough. They never put enough. It's always like, I'm eating ice here.
That's why it's fun to make them. You put as much as you want.
Ah.
So shape base is the way to go.
So before I drew the cylinder, was the shape okay?
Yeah, I thought so, and then you changed it.
Well, because the thing I wanted to get across is that the top of the cylinder, this corner of that edge of the cylinder is right at the edge of the ice.
Alright. I see.
It goes all the way from the bottom all the way to the top. And if I were to draw one that was wider, it would also go from paper up to ice. Alright? Alright. So what about the volume for this? Well, each cylinder has what kind of thickness? A dx thickness. Which means everything that I write in this expression is going to be going to have x's in them, not y's. Alright? What about the radius of that cylinder? Well, it's the distance from the y-axis over to the edge. That is a distance in x. So let's call it 2 pi x. What about the height of that cylinder? Well, the top of the cylinder is on the curve. The bottom of the cylinder is on the line. So this expression, 4 minus x squared minus x, is an expression that represents the height of the cylinder. And then lastly, for what values of x is this true for? Well, we've already determined that the smallest value of x for this particular region was 0, and you guys were supposed to figure out what the largest value was. 1.562. No, actually you should be keeping all the decimal places accuracy until the very, very end. 155. Okay. Yeah. And that's how we would set up that problem. Yikes-a-rooney. All right. I am going to be doing a ton of problems. I'm going to try to record a bunch of problems for you to look at, because the more exposure you get, I know it feels uncomfortable. This is always a very difficult section. All right. Even more so because of the break and because of MME. So, but here are the problems that I want you to start working on. And again, I'm going to also be doing a lot of problems with you. So, would you please get started on these? Some of these are just like, you're looking at the drawing, can you write an expression for the cross-sectional area? Some of them are full-blown, let's write the integral and calculate the integral for the volume. But I wanted you to start on these. And then we'll do a bunch of problems together tomorrow. All right? Yes. Then you will be watching. You'll be watching the videos online.
Is the quiz for
Okay.
7, 1, 3 still on Friday?
Okay. Before you leave, let me talk about the changes. I realize. Okay, this is 7.3. This chapter only goes up to section 5, and we're not going to do section 5. So there's only 4 sections, so I'm not going to do a quiz and a test. We're just going to do a test. But we'll do it, we maybe do it over multiple days. We're going to do something so you get enough practice so you can feel comfortable with this. All right? So we're not going to have a quiz on this anymore. I have a change of heart.